Welcome to the Deep Dive. Today, we're tackling something really fundamental in stats.
That's right, measures of central tendency. And we're kicking off with, well, probably the most famous one, the arithmetic mean.
Or just the mean, as most people call it. We've pulled together, mathematical explanations, some definitions, and quite a few worked examples.
Yeah, examples covering how you calculate the mean from just a list of numbers, but also when you've got data in tables, discrete counts, group ranges, the whole lot.
Right. And our mission here is pretty simple. We want to give you a really clear, practical grip on what the mean is, how it works in different situations. Think of it as a shortcut to really getting this concept.
Exactly, so you can walk away feeling confident about it.
Okay, so let's back up a tiny bit. Measures of central tendency. What does that phrase actually signify?
Well, think of them as ways to find the center or the typical value within a whole bunch of numbers. You have all this data, and these measures give you a single number that kind of represents the middle ground.
A summary number,
Yeah.
like the heart of the data.
Precisely. It gives you a sense of where the data clusters.
And the arithmetic mean, as you said, is the one most folks probably think of as average. How do we define it, technically?
It's actually pretty intuitive. It's simply the sum of all the numbers in your set divided by how many numbers there are.
Okay, sum divided by count. There's
Yeah.
a formula for that, right? A mathematical shorthand.
Yep. If you've got n numbers, say x1, x2, all the way up to xn, you add them all together. That's what the big sigma symbol, sigma means just sum up all these things.
Mm-hmm.
And then you divide that total sum by n, the total count. So the formula is just sum x and day.
So it's like if you pooled all the value together and then shared it out equally.
Exactly that. The mean is what each data point would get in that equal share out.
Makes sense. Our sources kick off with a nice, simple example. Can you walk us through it?
Sure. Let's say we have the weights of 5 people. The weights are 67, 65, 71, 57, and 45 kilograms.
Okay.
To find the mean weight, you just add them up. 67 plus 65 plus 71 plus 57 plus 45. That totals 305 kilograms.
Right. And since there are 5 people, you divide 305 by 5.
Which gives 61 kilograms.
Exactly. 61 kilograms is the mean weight.
Simple enough for a basic list.
Yeah.
But data often comes, organized differently. What if we have a table showing how often each value appears? A frequency distribution.
Ah, right. Yes, when you have a discrete frequency distribution, meaning specific values appear a certain number of times, the calculation changes slightly. We have a few methods. The first one is called the direct method.
Okay, the direct method, how does that work? What are the steps?
So you typically set up a table. You'll have a column for the distinct values, the variates, let's call them x. Then a column for the frequency f, showing how many times each x occurs.
Right, value and count.
And then a crucial third column where you multiply the value by its frequency. So f times x, or fx.
Got it. So for each value, you're calculating its total contribution to the sum.
Precisely. Once you have that fx for every value, you do 2 sums. First, sum up the frequency column to get the total number of observations. We call this sigma fy. That's like the n from before, the total count.
Exactly, it's your total count. Then you sum up that third column, the fx column, to get the total sum of all values, considering their frequencies. That's sigma fxs.
Okay, total frequency, total fx sum. Then what?
Then the mean is simply the total sum divided by the total count. Mean, anglais, is sigma fx.
Okay, let's make that concrete. There's an example in the source.
Yeah, let's take this one. Values are 5, 6, 7, 8, 9, and their frequencies are 4, 5, 3, 6, and 2.
Okay.
So we calculate Sx for each. 5 times 4 is 20, 6 times 5 is 30, 7 times 3 is 21, 8 times 6 is 48, 9 times 2 is 18.
Right.
Now sum the frequencies. 4 plus 5 plus 3 plus 6 plus 2 is 20. So sigma fy is 20.
20 total observations.
Yep. And sum the fx column. 20 plus 30 plus 21 plus 48 plus 18. That's 137. So sigma fx3 is 137.
Okay.
The mean is then 137 divided by 20.
Which comes out to 6.85.
Exactly, 6.85.
Makes sense. And there's another quick example just reinforcing that. Values 5, 15, 25, and so on.
Right. Values 5, 15, 25, 35, 44.5. Frequencies 14, 16, 20, 30, 20. Same process. Sum of frequencies, sigma fy, is $100.
Okay.
Sum of the xx products, sigma fx3, comes out to 27,450.
So the mean is 2750 over 100.
Which is 2750, or just 27.5.
Okay, so the direct method is, well, direct, but maybe a bit tedious if the numbers are big or there are lots of values.
It can be, and that's why we also have the shortcut method, or the assumed mean method.
A shortcut sounds good. Why would we use this one? What's the advantage?
It's particularly handy when the data values themselves are large. It basically simplifies the multiplication steps by letting us work with smaller numbers.
Okay, intriguing. How does it work? What's the trick?
So you still start with your table of values, x and frequencies f, but then you choose an assumed mean, let's call it a.
Assume a mean, like guess.
Well, not quite guess. You usually pick a value that's somewhere in the middle of your x values. It makes the next step easier. Think of a as a temporary reference point.
Okay, pick a central-ish value as a.
Then, for each x value, you calculate its deviation from this assumed mean. We call this d, and d equals xa8. You add a column for these d values.
So how far each value is from our assumed mean?
Exactly, and these d values are usually smaller, more manageable numbers than the original x's. Then you create another column where you multiply each deviation d by its corresponding frequency f, so an fd column.
Right, frequency times the deviation now, not the original value.
Correct. Then you sum up the frequencies, sigma fb, like before, and you sum up this new fd column, sigma fd.
Okay.
And the formula for the actual mean is mean equals a plus sigma fdd once. You take your assumed mean and you adjust it by the average deviation.
So you start with your assumption A and then correct it based on the average difference you found.
That's the idea. It brings you back to the true mean.
Let's try the example. Weights of 25 students.
Yes. Weights are 65, 66, 67, 68, 69 kilos. Frequencies are 8, 6, 4, 4, 3. Total frequency sigma ft is $25.
Okay. And the assumed mean?
Let's pick A, 67. It's right in the middle.
Makes sense.
So the deviations, d equals by 67, are 65, 67 is 2, 66, 67 is -1, 67, 67 is 1, 68, 67 is 1, 69, 67 is 2.
Okay, smaller numbers already.
See, now multiply by frequency f to get fd. 8 times the -2 is the -16. 6 times the -1 is the -6. 4 times 0 is 0. 4 times 1 is 4. 3 times 2 is 6.
Got it.
Now, sum that FD column, -16, 6 plus 0 plus 4 plus 6. That adds up to -12. So sigma FD equals 12, 2.
Okay, now the formula.
Mean plus sigma FD over sigma F. So mean equals 67 plus -12, $25.
Minus 12 divided by 25 is minus 0.48.
Right, so mean equals 67.48, which equals 66.52 kilograms.
Same answer as if we'd done it the direct way, presumably, but maybe with less heavy multiplication.
Exactly, especially if those weights were, say, much larger numbers. Calculating the deviations first really helps.
Okay, that's the shortcut method. But wait, there's another one, the step deviation method.
Yes, one more refinement. The step deviation method is useful when there's another pattern, specifically when all your deviations values share a common factor.
Ah, like if all the deviations are multiples of 5 or 10 or
Precisely. It lets you simplify the numbers even further.
Okay, so what's the extra step here compared to the shortcut method?
You start the same way. Find your deviations, d equals xa. Then you identify that common factor, let's call it I. It's often the difference between consecutive x values if they're evenly spaced.
Okay, find the common factor I.
Then you calculate a new deviation, often called t, where t equals dii, or writing it out, t equals xai would. You're basically scaling down the deviations. Add a column for t.
So we're dividing the deviations by this common factor. Makes the numbers even smaller?
Usually, yes, often down to small integers like -2, -1, 0, 1, 2. Then, just like before, you multiply this new t value by the frequency f, so you get an ft column.
Okay, FT column.
Sum up your frequencies and sum up this ft columns. And the formula is mean a plus sigma ft sigma f times I. Notice you have to multiply by I at the end.
To scale the result back up, because we divided by I earlier.
Exactly. You have to undo that scaling.
Let's see the example for this one, the one with values 10, 30, 50.
Right, values are 10, 30, 50, 70, 90, 110. Frequencies are 135 and 187, 240, 273, 124, 151. The total frequency, sigma f4, adds up to 1110.
Okay, assumed mean.
Let's pick A70 right in the middle.
Good choice.
The deviations by 70 are -60, -40, -20, 0, 24.
They're all multiples of 20.
Exactly. So our common factor I is 20. Now we calculate t by dividing d by 20. So two values are -3, -2, -1, 0, 1, 2.
Much simpler numbers.
See, now calculate NFT. 135 times -3 is -5. 187 times -2 -300 manager 4. 240 times 90 to 1 negative 0 times 0 is 0. 124 times 1 is 124. 151 times 2 is 302.
Okay.
Sum up that FD column. Set up 4 is 5. 374, 240 plus 0 plus 124 plus 302. That comes to negative 593. So sigma has T, magnitude some 593 I3.
Okay, got to calculate that. And add 593 divided by 1110 is about -0.534 times 20 is about -593 at 10.
Right. So mean is approximately 59.68.
Wow, okay, so 3 different ways to get the mean for tabulated discrete data. Direct, shortcut, assumed mean, and step deviation.
Yes, each useful in different scenarios, mainly to simplify the arithmetic.
Now, what if the situation is reversed? What if we know the mean already, but we're missing a piece of the data, like one of the frequencies? Can we work backwards?
Absolutely. That's a common type of problem. If you know the overall mean and have a missing frequency, you can set up the mean equation and solve for the unknown. It becomes an algebra problem.
Like solving for x, but the unknown is a frequency f.
Exactly. Our sources have an example, right, where the mean is given as 7.5.
Yeah. Values 5 through 12, all frequencies given except for the value 7, where the frequency is called f prime.
Okay. So you'd set up the calculation for sigma SXS and sigma FE, but you'd have terms involving 5 time. The sum sigma FXL would be some number plus 7FS, and the total frequency sigma FE would be some number plus $5.
In the example, it's $563 plus 7 FEs and 74 plus F for sigma FU.
Perfect. So the mean equation is mean sigma FX, which becomes $7 and 5 hours plus 7 FE, and then you just solve that equation for $5.
And then you just solve that equation for 5.
Yep. Multiply both sides by $74 plus FR, rearrange the terms, isolate $5, and you'll find the value.
And in this case, it works out that $5 has to be 16.
Correct.
Clever. And there was another one where the missing piece wasn't a frequency, but part of the value itself, involving a P.
Yes. Values 15, 17, 19, then 20 plus P, then 23. And we know their frequencies, and the overall mean is 20.
It's a similar idea, but the unknown P is inside one of the X values.
Right. You set up the sigma FX view calculation again. One of the terms will involve multiplying the frequency of 20 plus P by 20 plus P.
So you'll get a P dot or 2 term in there somewhere.
Potentially, yes. Or at least a term with P in it. You set the whole mean expression equal to 20 and solve for P.
The example mentions it leads to a quadratic equation.
It can, depending on how P appears, and when you solve it, you might get 2 possible answers for P.
So how do you choose?
You have to look at the context. In that example, I think P was related to a frequency, or maybe the value itself needed to make sense in the sequence. Sometimes one solution doesn't make practical sense, like a negative frequency.
Right. And here, the sensible answer for P turned out to be 1.
Yes.
Okay, so we've covered individual values and discrete frequencies. But a lot of data isn't presented as exact values. It's grouped into ranges, isn't it? Like 10 years old, 10, 20 years old, etc.
Exactly. Grouped data using class intervals. This is very common. And guess what? We have similar methods for finding the mean here, too.
Let me guess. Direct, shortcut, and step deviation.
You got it. The principles are the same, but there's one key adjustment we need to make right at the start.
Which is?
Since we don't have a single X value for each group, only a range, like 10, 20, we need a representative value for that range to use in our calculations.
Okay, what do we use?
We use the midpoint, or the mid-value of each class interval.
How do you find the midpoint?
Simple. Add the lower limit and the upper limit of the interval, and divide by 2. So for 10, 20, the midpoint is 10 plus 22 is 15.
Okay, find the midpoint for every class interval first.
That's step 1. Once you have those midpoints, you treat them as your X values in all the formulas we just discussed.
Okay, so for the direct method with grouped data.
You find the midpoints X, you have the frequencies F for each interval, you calculate the SX column using the midpoints, you sum up sigma F1 and sigma FXU, and then the mean is sigma FX. Same formula, just X is now the midpoint.
Let's use the age group example. 0, 10, 10, 20, 20, 30, 30, 40, 40, 50. Frequencies 10, 6, 8, 12, 5.
Right, midpoints are 0 plus 10, 2 is 5, 10 plus 22 equals 15, 20 plus 32 equals 25, 30 plus 42 equals 35, 40 plus 52 is 45.
Okay, those are our X values now.
Yep. Now fx, 10 times 5 is 50, 6 times 15 is 90, 8 times 25 is 200, 12 times 35 is 420, 5 times 45 is 225.
Got it.
Sum the frequencies. 10 plus 6 plus 8 plus 12 plus 5 plus 5 is 41. So sigma fx is over 31.
Right.
Sum the fx column. 50 plus 90 plus 200 plus 420 plus 225 equals 985. So sigma fx is 985.5.
And a mean.
Mean equals 985.41, which is about 24 and 1 41st, or roughly 24.02.
So the average age in that group is about 24. Useful for like public health planning or something.
Exactly. Understanding population demographics.
Okay, so that's Direct method for group data. Shortcut method, same idea with midpoints.
Same idea. Calculate your midpoints x. Choose an assumed mean a, ideally one of the midpoints or close to the middle. Calculate deviations FDFs using the midpoints for x. Calculate FD, then use the formula mean a plus sigma FD.
Just replacing x with the midpoint throughout the process.
Precisely. The example uses intervals 35, 40, 40, 45, etc. Midpoints are 37.5, 42.5, 47.5, 52.5, 57.5, one of the midpoints. Calculate D, midpoint 47.5, which gives netting is 10, netting is by 0, 5, 10. Calculate FD, sum it up of sigma FD equals 45.5. Some frequencies, sigma F equals $30.
Right.
Mean of 47.5 plus kind of made of 4, 5, 30. Negative 45 divided by 30 is negative 1.5. So mean equals 47.5, 1.5 is 46.
Okay. Could be useful for, say, a teacher looking at test scores grouped into bands. And finally, step deviation for group data. Still using midpoints.
Still using midpoints as x, still choosing an assumed mean a, still finding deviations dolly as x, NaO. But now, I is usually the class with the difference between the upper and lower limits of an interval, like 10 in the 10-20 interval, assuming they're all the same width.
Okay, so I is the class interval size.
Generally, yes. Then you calculate TAAI equals AAI, my I all A, AAAA. Calculate A of t, sum sigma F and sigma FTE, and use the formula. Mean A plus sigma FT sigma F times I.
Same formula as before, just with midpoints in class with I.
You've got it. The apple weight example illustrates this. Intervals 80, 85, 85, 90 grams, etc. Midpoints 82.5, 87.5. Assume mean A equal 97.5. Class size I 85.
Calculate EA, then FT.
Yep. Work through the steps, plug into the formula, and it comes out to 95.9 grams, rounded to 96 grams.
So the average apple weight is about 96 grams, useful for a farmer or a grocery store.
Quality control, packaging, pricing, all sorts of things.
And the crucial point, which the sources mention, is that no matter which of these three methods you use, direct, shortcut, or step deviation for the same group data,
you will get the same answer for the mean.
Right. They just offer different computational routes, potentially saving time or reducing errors depending on the numbers.
Exactly. Choose the one that looks easiest for the specific data you're facing.
Okay, that covers the how-to. Are there any, general properties of the mean itself that are good to keep in mind? Things that always hold true?
Yes, a couple of really useful ones. First, if you add a constant number, say p, to every single value in your data set, the mean of the new data set will just be the old mean plus p.
Ah, so if everyone gets a $1,000 bonus, the average salary goes up by exactly $1,000.
Precisely. Same applies if you subtract a constant them. The mean decreases by that constant.
Okay, that's handy. What's the other one?
If you multiply every single value by a constant number, say n, then the new mean will be the old mean multiplied by n.
So if you convert all the weights from kilograms to pounds by multiplying by 2.2,
the mean weight in pounds will be 2.2 times the mean weight in kilograms. Same works for division.
those are neat properties. Could save some recalculation time.
Definitely.
And just looking back at all these examples, weights, test marks, heights, wages, apples, ages, it really shows how broadly applicable the mean is, doesn't it?
It really does. It's fundamental because it gives that single summary figure. It helps us quickly understand a typical value, compare different groups or students in one class scoring higher on average than another, or track changes over time. Is the average income rising?
It boils down a potentially huge amount of information into one digestible number.
That's the core value of it.
Okay, so let's try and wrap this up. We've dived deep into the arithmetic mean. It's a key measure of central tendency.
Calculated simply by summing all values and dividing by the count for simple data.
Right. And for tabulated or grouped data, we've got the direct method, the shortcut or assumed mean method, and the step deviation method.
All designed to get you to the same answer, just sometimes making the journey, the calculation, a bit easier depending on what your data looks like. Midpoints are key for grouped data.
And we even saw how to work backwards if you know the mean but are missing a frequency or part of a value.
Yep, using algebra.
So it's a really versatile and fundamental tool in understanding data.
Absolutely essential.
Now, just to leave you with something to chew on, we've seen how useful the mean is, but think about this. What happens if your data set has one or two really extreme values? Like, imagine calculating the average income in a town, but one billionaire lives there.
Ah, the outlier effect.
Exactly. That one massive income could pull the mean way up, making it seem like the average person earns much more than they actually do. It might not feel very typical anymore.
That's a really important point. The mean is sensitive to those extreme values.
So it might make you wonder, Are there other ways to measure the center that aren't so easily swayed? Maybe something like the median. That's perhaps a topic for another deep dive. Until then, keep exploring.